Hi, I'm Andy. I'm here with Juergen to talk about the FTL project. This project is a product of a marriage between the open source WebKit project and the open source LLVM community. So FTL, that's for fourth tier LLVM JIT. Now you may be saying, did he just say fourth tier? Why do we need 4 tiers? Well, there's actually a good reason. I'm not just selling you new Razor. So let me give you a brief overview of WebKit JIT architecture. This isn't a WebKit talk, but this will give you context for what we're talking about. So there's a good reason for 4 tiers. The first one is called low-level interpreter because it interprets an internal representation of the bytecode. While doing so, the interpreter is profiling function entries, branches, types, everything that the higher tiers are going to need to optimize. So if you can see the chart at the bottom, it's showing you the amount of code that's being handled by that tier, the time spent in the tier, and the performance of that tier. So the interpreter is running all of the JavaScript code that's actually being executed. We want to spend minimal amount of time in that tier, so the green bar is non-existent here. And let's say speed is 1 for this tier. So now, after calling a function only 6 times, we're going to trigger the baseline JIT. So the baseline JIT is like the fastest code generator that you can imagine. All it's doing is taking the same instruction sequences that the interpreter would execute and splatting them into a buffer, stitching them into a static execution path. So good thing about having an interpreter and a baseline JIT is you can see here that we don't have to JIT nearly as much code. There's a lot of run once code, and we save a lot of memory not having to JIT all of that. So our blue line's much smaller here. Good thing also is that our performance is 10 times higher in the baseline JIT than the interpreter. So we're willing to spend 10 times as much time in that tier. And that's because it turns out that removing interpreter dispatch loop is actually really beneficial. And stitching together static execution traces works really well with modern hardware. It feeds all of the prediction logic. So we get great benefit already from having 2 tiers, but there's still a lot of opportunity. So we haven't done any optimization. JavaScript has a lot of abstraction that we need to do a better job optimizing. So that's why we have a 3rd tier. So 3rd tier is called DFG for data flow graph. It's called that because it's building an IR for the whole method, minus the parts that don't need to be compiled, some slow paths. So the way we get into that tier is we actually have to branch into an entry point or a pseudo entry point. And say if we're in the middle of executing a loop, we would do that through something called on-stack replacement. So OSR entry is a process of getting into the 3rd tier. Now, because we already have a good baseline JIT, we have plenty of time to do high-level optimizations. We can do inlining because we have IR for the whole method. And we can focus on a smaller portion of the JavaScript code base. You see our blue bar is getting smaller. And our green bar and yellow bar are getting higher because we're willing to spend more time in this tier and the performance is faster. It's 3 to 4 times faster than the baseline JIT because we're removing so much abstraction now just from high-level optimizations. So the story doesn't end there, though, because we're continuing to do profiling this whole time. And after we've inlined at a high level, we can get much more precise type profiling. So if we have an opportunity to recompile again with this information, we can remove even more abstraction. Not only that, but in many cases now we can remove so much of the abstraction penalty that standard compiler optimizations that you'd see in a static compiler are becoming more and more profitable to do. So that's why we have a 4th tier. 4th tier in case of WebKit is just the DFG front end for high-level optimization. But now it's generating LLVM IR, driving the LLVM IR optimization passes, and running through LLVM CodeGen. So now we're done with profiling. This is the best code we're going to get. But it only has to kick in on a very small portion of the JavaScript program. So the blue bar now is becoming tiny. This is workload specific, of course. If you have a lot of JavaScript programs are only going to run for less than a second. And if you don't make it to the 4th tier, you don't pay for it. You don't pay for what you're not going to use. That's fine. But for longer running programs, we expect you to spend most of your time running in the 4th tier. And the performance is, of course, going to be higher than 3rd tier, roughly 30 to 40% faster. OK, so I told you how we get into tiers 3 and 4. But we need a way to get out, too, because those tiers are doing high-level optimizations. They're doing lots of speculative optimization. And if those speculations fail, we need a way to recover. And the way we do that is a process called on-stack replacement, again. But this time, we're exiting from the higher tier back to the lower tier. And as I mentioned, the baseline JIT is just stitching together code sequences for each bytecode. So we can jump in at any bytecode location. OK, so now that we have our 4 tiers, how do we actually get the best code out of FTL? Well, the way we do that is the same way we get the best code out of compiling for any high-level language. And in my view, there are 3 steps to this. Step number 1, remove abstraction, obviously. Step number 2, emit the best code for the code sequence for very common operations. So when you're supporting a high-level language, you're going to have some common operations for very important things like field access, method dispatch. You're going to have a lot of things left over from step 1, type checks, bounds checks, overflow checks. It's very important to emit absolutely the best code sequence for these things. These are the critical path. And then finally, step 3, do everything else, all the compiler optimizations that you're used to. So in my view, you have to do these steps in order. It doesn't make sense to go to step 3 without getting the other 2 right. So how does FTL do these steps? So DFG does a lot of high-level optimizations, but the coup de grace, the thing that really matters, is speculative type inference. So the type profiling is telling us which type to expect at a given point. So a canonical example would be like the add of 2 variables. Is that an integer add, a double add, string concatenation, or it could be any arbitrary operation? Well, profiling tells us that and lets us generate the right code. So step number 2, now in the DFG already gets, the 3rd tier already gets step 1 and 2 right. It does a good job with this. It does that because it's a custom JIT. They knew what kind of code sequence they wanted for these operations, so they just had it generate that code. Well, in FTL, we don't have that luxury because we're going through LLVM backend. So how do we get exactly the right code sequence and support step 1, which is speculative type inference? And the way we do that is a new mechanism, a new LLVM construct called patchpoint. We'll be talking a lot about patchpoints. Finally, now that we have steps 1 and 2 right, step 3, do everything else, is the LLVM pass pipeline. It works surprisingly well once you get the other things out of the way. So now I'm going to invite Juergen up to tell you how patchpoints work.
Thanks, Andy.
Sure.
OK, so some details how patchpoints work. This one. OK. Yeah, so we actually have a pretty well-documented intrinsic. The patchpoint intrinsic, I think, is like the best documented intrinsic ever. And you had to write lots of documentation for this intrinsic. So the way we envision it right now, or the way also we how use it right now, is a patchpoint is basically a wrapper around a method you want to call, and with some additional information we need. So for example, we have an ID. You need this ID to later figure out, to have a correlation between what you emitted at LLVM level and later what to do with it. And so you can, because what happens is besides that stack patch points get removed, they also get duplicated later by the optimization passes. So you need to have some kind of mapping. You can't rely on the order you emitted them before. And the most important thing is how many patchable bytes you want, because that's where you do all your code optimization. We have a target. That's basically the method you want to call or function. Right now, it has to be an absolute address. Maybe in the future, we'll support symbolic call targets too. Then you have to specify how many arguments this function takes, because that means, in this case 2, the next 2 arguments will be call arguments, which will be passed on to the method. Everything after that is what we call the live values, or And these are values you want to record because you need to observe them. Because later on, when you have to restore your execution from a different part of the code, you have to first load these values to have a valid state. So how do they get lowered? So after lowering it to a machine instruction level and after register allocation, will look something like this for x86. So most of the things are just transferred. But we have to add, for example, the calling convention. Because based on the calling convention, we will record later different information in the stack map. The call arguments get lowered according to the calling convention you specified and your architecture you're compiling for. Some of them might be in registers, others might be on the stack. Yeah, depends on your architecture. In this particular case, the live values were already in registers, so we record the registers. If they have been on the stack, or if they're constants, then we record this information. We don't put them into registers and increase register pressure. We don't want to do that. And then you have the usual information that every call actually adds. This is also target specific. So we usually have the register mask and what gets clobbered, what is your return value, and we add a few scratch registers. We need these scratch registers later on to materialize the call target and do the jump. Plus, it gives you later on registers which you can use freely when you do the patching without having to spill them. So in the end, the only thing we generate is actually just a little bit text in your object file which materializes the call target and does the call. If you specify no call target, basically a null value, we won't even do that. It's important that you at least request as many bytes it takes to do this call, otherwise the compiler will yell at you. And what is also important on x86, we do fat knob optimization. That means you have to patch everything, otherwise you have an invalid state. Besides all this information, we emit an additional section. It's called the stack map section. And the stack map section records every patch point call site. It tells you where it is, so you know where you have to patch the code later on. And it records the locations of the live inset, which you wanted to, or the live values you were interested in. We also add some additional live out registers. This is an optimization pass we run that tells you what registers have to be alive after that patch point. That means when you patch that little location, you know which registers you have to spill and you don't. So you can optimize your code there too. And then handing off to Andy again.
Okay. So I'm going to show you some examples now of how patchpoint is used within FTL, and then talk a little bit about future design changes to patchpoint. So I'll have to go through some of these examples kind of quickly, but what I'd like to show you is inline caching. So this is an important use case, and you've seen this in the past for method optimizing dynamic dispatch, but WebKit has another use for this, and that's optimizing field access. So inline cache is great because it lets you embed a fast code sequence right in line with the compiled code. This is hard because in JavaScript, the shape of the object that we speculated can actually change at runtime. So on the left-hand side, you see an example where we've speculated that there's going to be a direct field access. So we patch in a code sequence that does a compare against the type of the object, jump to a slow path if necessary. If not, we just load from a field offset. And the encoding is a little weird because we want to fit in exactly the space that we've reserved. But now later, we may find that we speculate the type at this point such that the field access is off in secondary storage. It's not in the fixed size cell of the object. So the way we handle this is just patching over that code sequence. And it turns out that this is a common enough situation that we still want a fast path for this. So here again, we compare against the object's type, jump to a slow path, but then we have a sequence of 2 loads to do the indirect field access. So nice thing about inline caches is that if the speculation changes, we don't have to invalidate the code, which could be expensive and require us to recompile. So we handle the fast paths without invalidation or simply by patching them in place. So now to support inline caches, we added a new calling convention called anyReg. So because inline caches are right in line with compiled code, we want it to preserve all the registers, and it does that, except for 1 or 2 platform-specific scratch registers. But importantly, the arguments that you pass to the patch point and the return value are allocatable. So the register allocator is going to decide which register is most convenient for, say, the object that you want to access. Unlike the other live values, they can't be spilled, though, because we're not going to be able to reload these values in the patch code. Now, before I talk about other use cases, I have to introduce another intrinsic called LLVM Stack Map. But all this is a stripped-down patch point. The only difference is that it doesn't reserve space in line for patching. So if patching happens there, it could overwrite instructions that LLVM emitted. But it works well for invalidation points and for partial compilation. Just like patch point, it captures the live state and writes the stack map entry the same way. This doesn't need any calling convention or call arguments. And just like inline cache, it preserves all but the scratch registers. So let me show you an example of code invalidation points. So this is useful when we want to optimize making the assumption that this, we know the type and we don't want to check it in the future, just full on optimize for this type. The problem with that is, as I said before, the types can evolve over time. Now, as long as we stay executing in the optimized code that we generated, it's perfectly safe. But we may call out to a runtime call or method call. Type information may change at that point. And when we return from that, we need to know whether the optimized code is still valid. So at IR level, the way we handle that is when we see a runtime call or a method call, we just put a stack map intrinsic immediately after that. Now, when the code's emitted for the stack map, if you see in the example, right after the runtime call, it's just a label. So it has no real impact on code generation. Now, in this case, following the stack map, there's some arbitrary optimized code. Here, it's just an add. But when we emitted the stack map, or when we emitted the stack map intrinsic, we said we want 5 bytes for potentially patching. So we have to put a trap here if there's an invalidation event. But we don't want to patch over branch targets. And the reason being that we want to give the runtime freedom to not have to figure out, oh, what's the next invalidation point I'm going to hit? Instead, it's just going to say, oh, I have a type event, find all the stack maps that are invalidated, and just take a shotgun approach to shooting them all down, not knowing which one we're going to hit next. So in this case, we asked for 5 bytes. The add's 4 bytes, so we have to put a 1 byte no op there. Now, what happens when the type event is triggered? WebKit calls this a watch point. We just overwrite the add and nop with the long jump to a trap. That thunk will call into the runtime to do an OSR exit. We call this a de-optimization event because it's going to resume execution in a lower tier code, the baseline JIT. So now sometimes we want to be able to do a speculative check and not have to pay the penalty of invalidation if we're incorrect, and maybe the check is very cheap. So here's an example we see a lot in FTL of an explicit check. So here we just, at IR level, explicitly have a type check. If that succeeds, we fall through the speculatively optimized code. If it fails, at IR level, we just branch to a stack map in an unreachable block. Now, when we generate code from that, we just have a label, and then the JIT, before linking the code, will patch call to a trap right there in place. There doesn't need to be any dynamic patching because the patchings happen out of the fast path. So if the speculation fails, we branch to this call, which then thunks to the runtime to perform de-optimization. OK, so I've showed you some examples of how to use patch point for de-optimization. There's some interesting, if you know you're using a patch point for de-optimization, there's some interesting semantics that can be exploited. So for example, in the example I showed you before, what if that type check passed? Well, it's still safe to do the optimization. It's just not optimal. So in general, doing the de-optimization is safe at any point as long as the runtime has a stack map for that location. and usually wants a reason for the deopt so it can profile that. Similarly, we can deopt late if we want to, as long as there are no side effects. We just say, tell the runtime the location we want to resume, and the patch point naturally preserves all the state that's needed at that point. This is important because we need to reduce the number of patch points that we inject into the IR. There could be quite a bit of bloat. And using these semantics lets us do that. Now, if we raised the semantics up so that LVM could see them, we could even do this with an LVM pass. So I showed you examples of how FTL uses patch points, but I want to emphasize this is a generally quite useful feature. These are the use cases that we've gotten requests for so far. Dynamic relocation is the simplest. Just at runtime, we want to patch a target of a call to a different location. I showed you polymorphic inline caches where we want to emit a special code sequence right in line with the hot path. Patch points support 3 different kinds of de-optimization. Explicit speculation checks, invalidation points, partial compilation. And there's another use case that has been requested, and we don't use this in FTL, but GC safe points, which the last talk was about. And Philip and Sanjoy have been implementing something called a state point, which is based on the same infrastructure. And that gives the runtime enough information to perform precise garbage collection. So informally, we've been talking about what we can do to patch point to improve it, and it's been an experimental status for a year. We need to make it a first-class intrinsic so it's stable for people to use. I'll just mention a few of the things we want to do with it. So as I said, we have this stack map intrinsic. That doesn't need to be a separate thing. We can have one intrinsic. We can use call attributes to select behavior. So for example, we can just say this is a destructive patch point. Another thing that's happening is someone just recently added Invoke Support. And Kevin, I don't know if you're out there, but wave if you are. So that's a great enhancement. Philip and Sanjoy have been talking about adding support for symbolic targets. And this is powerful because if the optimizer can say, oh, I'm calling this recognized lib call, it can actually optimize the call just as it would other lib calls. And then another thing I'd like to propose is adding a condition to the patch point to allow us to do more aggressive optimization. And I'll show you an example of that. So here's an example where we have code using patch points. And I'm using this new technique of giving the patch point a condition. So you'll see 2 patch points, one outside of a loop, one inside the loop. So the patch point outside the loop is given condition A. And what I want that to mean is that if condition A is true, you've got to call into the runtime at this point. And we're telling the runtime you're at location 1, and this is the state for location 1 before the loop. Similarly, there's a check inside the loop on a different condition, condition B, and that's a different bytecode location and different state. Now, I don't like patch points in my loops, so I want the code to look like this. And I can do that as long as I can find a condition that implies both A or B. It's logically equivalent. Now, what happens if condition B is true? I know we're never going to enter the loop, and that's fine. I tell the runtime I'm at location 2, or location 1. I give it the state for location 1, and it knows what to do. And worst case, we've de-optimized a little bit early. But what happens now is I don't need to maintain all that live state through the loop body, which is very useful. And I don't have a check inside the loop, so I can do a lot more aggressive loop optimization, maybe even vectorize the loop. And we have enough time now to hand it back to Juergen. So thanks.
Yeah, so I'm now going to talk a little bit of how we used LVM to optimize the code generated by the FTL. And for that, I want to first talk a little bit about how this code looks like, because it's a little bit different than your usual C, C++ code that gets loaded to LVMIR. So you don't have to read the instruction. The important thing is we have lots of small basic blocks. And because we have all these checks in there which go to stack maps, stack intrinsics. Another thing is, to do the type checks, we normally check the upper 16 bits, which is the tag, and that is a large constant on x86. So we have many large constants which happen to be always the same in each basic block. Also, by the time we JIT the code, we know where all the objects are in memory. So we don't use relocations, we use the absolute addresses of them. And the interesting thing is, they're very similar. they have like just small minor offsets of each other. And besides that, we have some arithmetic with overflow checks, because we have to check for overflows in JavaScript. And obviously lots of patch points in stack maps. So that's how code normally looks like. And that was a problem actually for LLVM. At least the constants was a problem, because selection DAG compiles a basic block at a time. And was basically rematerializing the same constant over and over again in the same for each basic block. Since we have many small basic blocks, that's lots of overhead. Also, materializing all these different addresses for these objects also very costly. So because of that, we added a constant hoisting pass into LLVM, which tries to work around this limitation. So basically, it recognizes those common constants, hoists them into the common denominator. And for similar constants, we use a base constant, and then we use some arithmetic to materialize it. And that nice addition normally base pointer plus offset can be nicely folded into loads and stores later on. So that's zero cost later on. And we work on a whole function level when we do this optimization now. So compared to DFG, which was only doing this on a basic block level, we actually get even more benefits doing that. Plus, it also should help generic LLVM code that has this problem coming from C or C++. So for FTL, we only used a reduced optimization pipeline because we care about compile time. But we got really nice benefits from just using inscombine and simplify CFG and GVN, all this stuff, because once we lower the DFG IR to LLVM IR, there are some redundancies there. Plus, once you lower it further, there are additional redundancies we can eliminate. So that was very helpful. We have TBA for all our loads and stores. We have very good type information. So there shouldn't be any aliasing problems. So we can optimize it a lot. And then we have our code gen, which with the very good code generation, instruction selection, we generate better or optimized instructions. And register allocation helps a lot too. We get rid of a lot of unnecessary moves for coalescing and have less spills than the DFG. So in the end, we have really good code thanks to LLVM. But generating really good code takes a lot of time. And in the JIT, compile time is runtime. So that was, it was taking way too long. For example, here, this is just code gen compile time, which accounts for over 60% of the overall compile time. Our reduced optimization pipeline only needed 30% of the compile time. So this is, that shouldn't be. And you can see on this slide, for example, like we spend a ridiculous amount in instruction selection. Selection DAG, we should replace it. I think everyone agrees here with that. And so we did experiments. We used fast ISL. We optimized fast ISL to generate better code. And instant drop of 45% compile time. Mind you, this is actually on ARM64 having the same code quality for JavaScript. So there's no performance penalty doing that. It's only pure compile time improvement. An interesting problem is because of all these stack maps and patch points, and we keep track of the live state, the greedy register allocator has a really hard time with that because there's lots of splitting now going on. And we are spending a lot of compile time, code generator, just in register allocation because we have the splitting issue. We used Andy's like 2 or 3 year old basic register allocator now, which hasn't been used, I think, for a while. Or ever. It's dormant in the code base, but hey, it still works. And it doesn't have that issue. And interestingly, when we did some performance benchmarks, at least for architectures with lots of registers, didn't seem to be an issue. There's no more spills, or it was not a performance issue. So we reduced the compile time a lot again. And MI schedule, we can remove that too, but that didn't give us much. But basically, we were able to reduce the compile time by over 60% just in CodeGen by optimizing these parts. And there's still things to be done. For example, the machine dominator tree. Like, we computed 6 times in the CodeGen, so there's something wrong with this. So maybe someone wants to tackle that. And Yeah, there's lots of other stuff going on. I think the next thing you can also look at is the optimization passes now. So we're first scanning for the biggest offenders in the pipeline, but it shows LVM as a JIT, we still have to work on it. Even if we reduce the passes, or there's still we have to actually consider compile time more. We have to optimize our passes. And yeah, so I think that's what we're going to work on in the future, is make the whole infrastructure better for everyone. Yeah.
Okay, so that's it for our talk. I've listed some important references, though. I talked about the JIT architecture, and Philip Pislow has a great blog post on that. He also gave a lightning talk last year's LVM Dev Conference. I also have an LVM blog post on FTL that has a little more detail. In there, I talk about things we want to do better with the MC JIT and CAPI that we didn't talk about here. So there's a lot of documentation on how patch points and stack maps work. That's already in the Lang ref. It's been there. I'm working on a proposal that I'm going to send to the dev list very shortly, I promise, for the final form of patch points, what we want them to look like. There's a lot of interest in that. And finally, all the implementations there in LLVM, Juergen and Lang Hames both worked on it, so they're available for questions, right?
Lang is over there, so
and
all the JIT guys can go to
yeah,
him.
Lang gave the BOF earlier this morning on MC JIT.
Yeah.
And if you have any questions now, I guess we're ready to take them.
Okay, let's go ahead and thank the speakers.
Easy one. Juergen, the last slide on your breakdown of performance.
Yeah.
So this is quite beautiful. What is the relationship to code quality?
As I mentioned, we worked a lot on fast ISL. And this is only for ARM64 now, but we actually got to a point that the code we generate, at least in case for JavaScript, which has, looks a little bit different than what you could normally get from C++, but at least for that case, we create the same or better code with fast ISL. But I have to say, we don't do vectorization yet. That means, once we add vectorization, it gets way more difficult with fast ISL. But I guess in this case, we can drop back the selection tag for now. But yeah, this is basically, it means you get all the compile time improvement with no regression in performance.
Yeah, now for the register, allocator, and scheduling pieces, writing a target independent backend is hard, and there's a lot of infrastructure to deal with the outlying cases. And right now, we're just not hitting those cases, so we don't need all that complexity.
I have two questions. So first, looks like you customize the JIT. So is that exposed API or just the internal?
That is the same API everyone else uses. WebKit or FTL uses the public available LVM API, which is in trunk. So we have no extra stuff in there.
Okay. The second question is that are you using the MC JIT based on that?
Yes.
And are you using multiple threads with that?
We use that too, yeah.
So it's pretty stable.
We have released software with that, and it's very stable, yeah.
Okay, thank you.
Yeah, as Jim said in the BOF, it's as stable as any
Yeah.
multi-threaded LVM. It's really whether LVM code generator is multi-threaded, and it is supposed to be, and it seems to work. So, yeah.
So I just want to ask on the compile time slide again, what were the absolute times we're talking about here for one of these compilations?
I don't like to say that.
Okay.
Yeah.
That's why we have 4 tiers.
Yeah.
So you mentioned that you haven't turned on the vectorizer yet. Would the presence of patch points in the loop prevent any vectorization from happening?
Yeah.
That's actually one of the reasons we haven't enabled it yet, because there wouldn't be a point. It wouldn't work. So that's the reason we want to first, combine these patch points if possible, and then even more important, remove them or move them out of the loop, so that for like the vectorizer is able to vectorize it.
So, I mean, I'll just say that the DFG can remove a lot of cases where we would need patch points. And there are loops where it can remove all of them. And we can potentially vectorize those cases. We haven't turned it on because it wasn't the most important thing at the time. But being able to optimize patch points, as I mentioned, and hoist them out of loops is going to allow much more vectorization. Yeah.
In practice, do you see a lot of loops where patch points have been hoisted out?
Well, I mean, the DFG does do if it wasn't doing high-level optimization to remove checks wherever possible, it would be problematic. But again, we still have, the code is still full of these things. And the overhead, that's why we made the overhead low. And it doesn't interfere too much with optimization. Like I said, with vectorization, we need to be able to hoist them out of loops. So, yeah.
So it's a beautiful graph, but it starts at 25%. What is below 25%? Is it miscellaneous? So what is taking this 25%?
That list is huge. We have lots of code gen passes, that run afterwards, which at the beginning didn't seem important if you look at it, elephant in the room here. But now at the end, they become more important. And what you basically see there is there's SM printer, all the small paths that run afterwards. Normally they amount for 1% of compile time at most, but there are many of them.
I think the other answer that you gave earlier is that, well, now that we're at this point with CodeGen, this doesn't include the opt passes. This doesn't include higher level passes. Yeah. Those need to be improved.
Yeah.
How about the code generation for patch point? You currently have indirect call. You use a move of 64-bit value, and then you do the indirect call.
Yeah.
Is there a reason for this? For example, if you know that if you have a small code model, your destination will be within 31-bit offset. Can you just use the direct call?
So since we don't support symbolic addresses yet,
right,
we don't do that. But once Phil adds that, I'm pretty sure you can consider the code model and then create better code for that. Plus, you have to also, if you think you can do better, just give it a null target now and patch it yourself. So that you always have that option.
I should mention that WebKit doesn't use the target. It's always a null target. It decides how to emit code for the call.
Okay, thank you.
Any other questions? So everyone's ready for lunch. Let's go ahead and thank the speakers again, and then it'll be lunchtime.